All right, good afternoon, everybody. Thanks for your time coming out today. I'm going to change things up quite a bit. I'm going to talk about bridges. Everybody else seems to be talking about buildings or research. I'm going to talk about really applied engineering to bridges and the effects of evolving service vehicle loads on the serviceability of concrete bridges. So HNTB has access to an extensive amount of way and motion data. And one of the things we noticed, particularly after the pandemic and with the increased cost of fuel, when we looked at the percentage of overweight trucks, you could directly correlate that number to the price of fuel. So as the price of diesel fuel increased, the truckers were more and more willing to put more weight on their trucks because it's more economical to pay the fine for being overweight than over the course of a fleet than to pay for extra fuel. So what I'm going to do in the course of this presentation, talk about the standard AASHTO loading. How many people here are bridge engineers who work in transportation? So just a couple of us. So for the people that aren't bridge engineers, AASHTO is the American Association of State Highway Transportation Officials. They're the ones that write the guidance and requirements for vehicle bridges in the United States. Then I'm going to talk about the WIM data, how we evaluated it for one specific site, what our results were, how does that impact our serviceability of our bridges, and then finally some conclusions. So the design truck that we use in AASHTO is called an HL93. It's got an 8-kip front axle, 32-kip rear axle. The spacing of the rear axle can be varied. We got a little dance music going here. All right. Or a design tandem, which is 225-kip axles with a 4-foot spacing. And then finally, that's combined with a lane load, which is a uniform load across the entire lane or portions of that lane that maximize the effect. A couple of things that are important to note about this design loading. It was developed using WIM data from 1975, from truck data from the Ontario Ministry of Transportation. They had a database of 9,250 trucks, intended to generate a 75-year design period. It was calibrated for 2 lanes, so we use a multiple presence factor of 1 for up to 2 lanes, and then as you have more than 2 lanes, then you have a reduction factor. It was calibrated for spans up to 200 feet, so I'll focus my analysis of the WIM data on spans that are up to 200 feet. So again, what we're seeing on our bridges is that the loads often exceed what the design loading is. And as an example, this is the Alexander Hamilton Bridge. This is in New York City, goes over the Harlem River. And it's a longer span arch bridge, but this is where we got the WIM data from. So for the longer span bridges, as we'll see later in the presentation, they're not as affected by the single truck as much so as the lane loading or combined loading. But the impact on shorter spans, as you'll see, is going to be very significant. But just so you know where this data came from, this is New York City. That's the Alexander Hamilton Bridge. I have a pointer here. No. No pointer? Oh, turn it off. There you go. All right. Anyway, moving on. So we took the data from 2016. Over a 1-year period, or 1 year and a day, 366 days, or maybe it was leap year, we got an extra day, I don't know. But this is what our WIM guys gave me, 366 days, 7 million trucks, not 7 million vehicles, 7 million trucks went over this bridge. So our average daily truck traffic was almost 20,000 vehicles. So when you look at some of the numbers, with that amount of traffic, you know, something would say, well, I only exceeded it 1% of the time. Well, 1% of 7 million is still a really big number. So what did we do? So we have the WIM data for the year, 7 million trucks. We used a line girder method and line girder model. We looked at the WIM data to create the maximum positive moment and the maximum negative moment effect, which is the WIM plus an impact factor. WIM truck plus an impact factor. We did not assume any more than 1 truck, especially for longer spans. You could have multiple heavy trucks. This was a very simple brute force method. We just want to say for each one of those individual trucks, how does that compare to the design load from the code? So then to get bias factor, we looked at the HL93 design moment that you would use, both for positive and negative moment. And then we divided the WIM load by the HL93 load, and anything greater than 1.0 means that the weight of that one vehicle exceeds the design load from AASHTO. From a big level, high level picture, 4% of the trucks going across that bridge were greater than 80 kips, which is the legal load. So 4% sounds kind of small, but again, 4% of 7 million trucks is a lot of overweight truck passages on that bridge, well exceeding sometimes what the load was expected to be. So in our methodology, we looked at 40-foot, 60-foot, 80-foot, et cetera, up to 200-foot spans. We looked at 40-foot simple span, and when we say 40-foot composite span, or continuous span, I should say, it was two 40-foot spans. If you look at the data on the left, these are the bias ratios now, so anything less than 1 is good, and you look at that and say, oh, look, there's hardly anything, there's nothing above 1, or so it seems, right? But if we blow it up and look at the graph on the right, so now we're looking at just the vehicles that exceeded the design load. So there was 32,243 for the positive moment and 16,361 for the negative moment. So what that means is if I'm on an approach bridge that's leading up to this longer span bridge, in 1 year, the design load is being exceeded 34,000 times. But now let's look at the longer span, say 200 foot. So this is the other end of the spectrum. We did all the ones in the middle. I don't have time to look at all of those individually. But again, on the left is all of the trucks. That's all 7 million. Zoom in on the ones that exceed the bias ratio is greater than 1. And now it becomes this really small number, 191, and only in a positive moment. In the negative moment cases, we didn't have any exceedances for the 200-foot spans. Looking at the whole group of numbers, again, quite a few cases where we're at the shorter spans, positive moment, you're seeing quite a few trucks over that weight. It goes down as the span increases. For the negative moment, not as much as the positive moment, but still there's quite a few, particularly in the shorter span ranges. So why does all this matter? So when we're designing for the service limit state, we're trying to do two things, right? We're looking at the flexions and vibrations we talked about in the previous presentation, the effect of vibrations, how that makes people uncomfortable. So same thing on our bridges. If you're going across a bouncy bridge and you're driving in a vehicle, that could be discomfort to the driver, or oftentimes we have sidewalks. Then the pedestrians on the bridge would feel discomfort from excessive vibrations. We used to look at deflection for that, control for that, and the reality is vibration is much more important than the deflection. And the other thing is crack control. So whether it's a reinforced concrete bridge or a pre-stressed concrete bridge, we want to try to control the cracking in those members. What we do is a little different for each type of bridge. But again, in the interest of time, I'll leave it at that. So ACI 343, which I'm the current chair of that committee, this is our guidance document, analysis and design of reinforced concrete bridge structures. So these are the limits for different cases for flexure, for shear, of our allowable stresses, right? And this is for reinforced concrete. So our service load stresses are flexural stresses in concrete at service load after allowance for all pre-stress losses should not exceed the following: for compression 0.4 F prime C, tension and pre-compressive tensile zone with bonded auxiliary reinforcement 0.6 F prime C, with bonded auxiliary reinforcements to called cracking but exposed to corrosive environment 3 F prime C, and without bonded. So if it's purely pre-stressed, we want zero tension. So why is this important? So I'm trying to keep that crack small or no crack, right? Zero tension means no cracks. So that crack opens up. Our bridges are in very severe environments. Now that's an opportunity for corrosion and deterioration to take over. So the fact that we're seeing that these loads that far exceed the design loads and what we're looking for at service limit state is telling me that that bridge is going to deteriorate much quicker than what we expected. Similar AASHTO LRFD, which is what most bridges are designed for. You have service one, which is a load combination relating to normal operation of the bridge with 70-mile-an-hour wind to control crack width in reinforced concrete structures. And then service 3 is a similar case where we're objective of crack control and critical tension of segmental concrete girders and pre-stressed girders. So again, we're looking at crack control and we're looking at deflections. I'll skip over the details of those equations in the interest of time. Crack control is permitted under service loads with a crack width, fatigue of reinforcement and corrosion. Should be investigated in accordance with the provisions of Article 5.5 and 5.6. And compressive stresses shall be investigated using service limit state load combination 1. And again, very similar to the ACI limits, AASHTO has very similar limits. And I'm just going to skip over that. So again, why does all this matter? There's been multiple projects out there from NCHRP, recalibration of the LRFR live load factors in the AASHTO manual for bridge evaluation, NCHRP 2007, load rating for the fast act emergency vehicles, EV2 and EV3. So those are two national level projects looking at recalibrating that design load. And we've done several cases for owners, particularly for long span bridges, where we've developed custom design live loads so that when we're putting $1 billion into a bridge, we want to make sure that that bridge is going to last 75 years or 100 years or more. So we want to make sure the loads we're designing for are the appropriate loads. We don't want to over-design it, and we don't want to under-design it. We want to make sure it's designed to an appropriate load level. So we'll do a site-specific WIM analysis, collect all that data, use a probabilistic method to determine the probability of having multiple heavy trucks on the bridge at the same time, and come up with that custom load. So we've done that for Gothel's Bridge, for the Port of New York, New Jersey. We've done it for Louisiana DOT, New Jersey Turnpike, Oklahoma DOT, UDOT, et cetera, and also for the pavement side, equivalent single axle loads for pavement damage studies for New York City DOT. And finally, in conclusion, overweight trucks with short wheelbases are likely to create problems in short span bridges for the service limit state. Again, not so much for the longer span bridges. When actual loads exceed the design load, the performance of the structure can be compromised. Excessive deflections and vibrations can cause discomfort to drivers and or pedestrians. They can compromise joints and bearings. If you have too much deflection, it could hurt the performance of your joint, have it wear out quicker. And excessive crack widths can compromise the durability and impact the appearance of the bridge. Using WIM to categorize actual loading will lead to improved structural performance. All right, so that was the 15-minute version of my 25-minute presentation.